Are we starting? Not yet. Okay, so looks like we start our translation. So today our final lecture of our mini course, and let me share my screen. Okay, do we see it now? I assume yes. And so now you should see my screen. Okay, we are starting. So today is our lecture number 3, and the course is on verification of smart contracts on the Ethereum blockchain. And our first lecture was devoted mostly to general introduction to verification, and you can find the recording on the web. And then the second lecture discussed the basics of Ethereum platform and distributed applications and Solidity. And today we conclude with just to make the picture together, and we will speak about how to apply the formal verification techniques to Solidity contracts. And okay, just to repeat some maybe obvious comments, that surely the field is quite huge and it's impossible to get complete understanding during just this small course. But anyway, I hope it's useful because it may give you some basic ideas and insights into this field. And also I provide you a lot of comments and links and okay, in the era of search engines and internet, it's enough to have just keywords. So once you have a keyboard, this is just enough to find a huge amount of relevant information and to study what you need to get better understanding of the topic. So, and let me start from just a small comment about some specifics of Ethereum. And picture on the right is rather typical illustration to what we call a firewall in local area networks. And you should understand that almost in every reasonable situation, almost reasonable information technology system, almost any application which has some business value, it always runs under some firewall to protect you from attackers from the internet. So not everyone can access your protected area, but this is not the case for Ethereum. Because what's written on the left, due to openness of Ethereum, both programs and users can call into the public methods of other programs. And this is one problem, that everyone can access and call your code. And okay, this is not a good piece of information, but the other problem is even more serious, that it's really impossible to keep in mind all possible combinations and compositions of trusted and untrusted code. So the possible scenarios are actually unlimited. And this makes really a problem for systems like Ethereum, because everyone can access, everyone can call your code, and everyone can combine your code with some different code. And so basically the protection which you always have for like a firewall is not available here. That's one reason why we need some additional techniques to ensure everything related to safety, security, and etc. Another important point is financial risk. I like this picture on the right. When you definitely make say that, okay, on the scales, we put a lot of money for this system, for this testing, for this kind of different verification, etc. But the risk on the other hand, could be even bigger, because even now Ethereum runs smart contracts which manage millions of dollars, and that's why the security is highly sensitive. So to summarize, the goal of all this verification and yes, thank you. So now I can see your comments and questions on different screen. So feel free just to ask and comment. Maybe not today, but tomorrow I will answer everything during the questions and answer session. So okay, this slide is about different issue which is related to huge amount of money which are run by smart contracts. It's another reason to have more advanced technique for verification and validation. Okay, and before we go to some description of software verification tools focused on Solidity, let me give you a couple of very simple but anyway very important examples of more or less typical errors which okay, like any error, it's not good for your system, especially if it's critical. So the first example is about stack overflow error, and the idea that initially the call stack of Ethereum virtual machines had some maximal limit, which is 1,000 frames, and once the stack is reached, it causes some exception. The function call will fail. And this leads to an attack, which is described in the second passage. And the two keywords here are almost fill the stack. So the attacker doesn't have to fill the stack completely, but it could be almost filled. So your contract could be kind of start executing in almost okay context. And then it might happen that you get this exception, and if this exception is not handled or mishandled, then it may lead to the full stack failure, and this is kind of one source of vulnerabilities. And is it written here, like 5 years ago, Ethereum introduced some update. So currently, this attack is not relevant anymore. But in general, it gives you some idea, like some very simple procedure, like the calling another function could lead to a problem. And let me just go maybe into more details for those who don't understand the idea of call stack. Let's see some very simple example on the left. So you see function 1, which has some call to another function, which is called 2. Then function 2 calls another function, which is called 3. And then function 3 does something else. And surely this is a very much simplified example, but this is a very typical situation when you call some function. It's hidden from you, so you expect that it does something, but actually it does very little, and then calls another function, which calls another one. And what happens in memory? So you see step 1, 2, 3, 5, 6. So on the first step, once you call function 1, it's stored in the memory, and the processor, the virtual machine, tries to execute it. And once it reaches this line where function 2 is called, then you see step 2, you have in the memory the first function is still in the memory, and another one is added over it. So on the step 2, call stack consists of 2 functions, 1, 2. And then when 2 is executed and the virtual machine reaches this line 3, then the other function, which is called 3, is introduced into the memory. So at step 3, the call stack consists of functions 1 to 3. And then once 3 reaches its terminal point, it's completed, then it's removed from memory, then we have 1, 2, then 2 is finished, then we return to n, and then finally, when function 1 reaches its endpoint, the memory is empty. So you see, this is kind of very simple idea, but you definitely had to keep this in mind that once you working with your source code, with your smart contract, that memory could be quite complicated. And as I already mentioned, this is what I am saying now is only about your own contract, but it might happen that at this point you call some external contract and you don't really know what's happened there. So the combinations could be really unpredictable. So that's the reason why this is some advanced technique like formal verification need to be applied here. Okay, let's go to different example, and it's related to arithmetic bugs. And from one hand, you might say that arithmetic is always simple because typically, especially in functional applications, you don't have advanced algebra and calculus. Usually, you just use additional multiplication and that's it. But what you need to keep in mind that there are different limitations on integer data types, and the violation of these limitations may lead to some problems. And on this slide, you see some screenshot from Solidity docs with explicit warning that integers in Solidity are restricted to certain range. So in your intuition, you always think like integer is a variable which can have any value, like 1 is okay, 10 is better, like 5,000 is possible, and 10 millions is okay. But in real applications, you always have some restriction. Like in this example here, you see u int 32 means u means for unsigned. That means that all the values stored in this variable will be only positive, and 32 indicates the number of bits which will be used in memory to store your integer number, and that explicitly means that you have some kind of upper value, upper bound for this value, which is 2 in the power 32 minus 1 because we start from 0. And if you try to store something bigger than that in this variable, then you will have some problems. And similar situation, if you try to store even small but negative number in variable of this type, again you will get some problems which could lead to some serious consequences. That's exactly what you need to aware of. And natural question which people usually ask, why then we need all these different data types for actually the same like integers? But the reason is very simple, is it's about memory. So if you need to store just a couple of bits, but for every variable you have like a huge number of bits, then that will be very inefficient. That's why every programming language actually has different types for integers, just to be more efficient with memory. So, and this is kind of another type of bugs which are, okay, they are quite simple from kind of a logical point of view. So there is no complicated business logic inside. But anyway, it's quite easy to forget about these limitations or just not specify it explicitly. So the other guy who will code over your library will not know the explicit limitations, and that will lead to some problems. Okay, and again, just let me remind that we are speaking about financial applications. So losing some number means losing some huge, sometimes, amount of money. Okay, so let's switch to the main topic today, and it's about smart contract analysis tool. And I'll start with Oyente, and Oyente is quite well-known tool. It's almost more than 5 years already and old, and it was released by a National University of Singapore. It's written in Python and uses Z3. And okay, I hope now you know well what Z3 is. It's a soft satisfiability modular theory solver, which we discussed during the first lecture. And the idea is it's based on symbolic execution over the bytecode. That's really important. We'll speak about it in a couple of minutes. And so you provide to this tool both the source code and bytecode. And then the tool targets 4 different types of bugs, like transaction order dependency, timestamp dependency, mishandled exceptions, and reentrancy. So this is, let me maybe add some comments here. So let me remind you that formal verification is about checking the properties of your code against the specification. So there are kind of 2 different main scenarios of using formal verification. The first scenario is exactly what we have here. Once you have very standard requirements, like you have very typical bug, which could be formalized as some set of rules, and then you take any piece of code, you already have this specification, which is exactly the check for these bugs, and then you use this specification, use this code to check the code against specification and approve that indeed this code fulfills all the properties, that so there is no bugs like this exist. So this is one scenario when you have all the bugs already predefined. So, and this scenario is quite popular because it requires nothing from the developer to use this tool. So you just put your piece of code, you run your tool, just push one button, and then you immediately get the results. And the other scenario of using for formal verification is when you have very specific business logic and you need to check your code against this business logic. Then it requires you much more time and resource to do with it, because you need time to formalize your business logic and then maybe to apply formal verification to this business logic. And this is a different scenario, so we will speak about it today. So today's example all about first scenario when you have tool which is specifically targeted at very specific types of bugs, like written here. And here is the link to GitHub. So just go to download it, to install it, and to play with it, because it's open source. And okay, how it works. This tool has 4 components. And the first one is control flow graph builder. Like I already mentioned, it's based on bytecode. So it converts bytecode into control flow graph. Then the second stage simulates the behavior of these instructions of this bytecode and uses Z3 prover to decide to analyze the path conditions. Then once you get these path conditions, you can check for these 4 types of bugs. And finally, you need additional stage to validate some maybe suspicious scenarios or values, just to reduce the rate of false positives. Okay, our short course is probably too short, but anyway, I'll try to make sure that you at least understand everything what's written here. So I'll start from the more comments about what is actually bytecode. So let's start from, so anyone who writes a Solidity contract starts from some integrated development environment, then you create your source code, then you compile it. And so the source code is compiled into bytecode, which is actually a low-level machine language that gets executed by the Ethereum virtual machine. And I like the picture which is here. So you see the first stage is the topmost layer. So you start from code, right? You write it in Solidity, and then you call compiler. So compiler creates bytecode, and here is example. So bytecode is not human readable, so it's just, as you see from the title, it's just sequence of bytes, but actually it's just some basic commands of the machine. So you have this bytecode, but what's important, bytecode is independent on your hardware. So, and that's really important. So bytecode is optimized. It's already very close to executable file, but it's not really executable because you might have different hardware. For some people run his or her node, I mean Ethereum node on one operating system. Other people have different. This guy has kind of two processors, another one has one, etc. So this bytecode is finally deployed to some network. In this example, it's a test network for Ethereum, which is actually runs on different nodes here. So these boxes are actually different computers connected to the Ethereum network. So, and okay, that's basically the idea. So you start from source code, you compile it into a bytecode which is universal for all the participants of the network. Then this bytecode is sent to your machine, and you have already this EVM installed on your machine, and then Ethereum virtual machine runs this bytecode. So actually now I assume you understand this, at least half of this first sentence. So you have bytecode, and then you need to build a control flow graph. Okay, let's see what's control flow graph. This is an example of, this example is actually from Java virtual machine, but doesn't matter. So as I mentioned, bytecode is almost the executable file. So it consists of very small steps, very simple instructions to your machine, like here, like some assignments, some memory access operations, etc. So most of them are executed sequentially. So you apply first statement, then second, then third, etc. But at some point, surely you hit some branch. Either you go to the right or you go to the left. You see, number 6 here is some if statement. So if something is correct, you go to block number 2. If it's not, if its statement is not true, then you go to block 3, etc. So this is actually a very simple idea. So you have sequential blocks. So every block is just sequence of some statements, of some commands. And once you need some branching, you have a link to a different block. So some blocks are the small, some blocks could be larger, but basically you can clearly visualize the structure of your program as this graph. And what's important, that this graph could be built automatically. So you don't need any human involvement into this this stage. So that's actually what happens here on the first step. So what IONTA does, it takes bytecode of your smart contract, then it automatically analyzes it and converts into this graph structure, which is called control flow graph. So then we apply the tree for symbolic computation over this code, and this is basically the idea of symbolic execution. So in kind of numeric execution, what happens? You go step by step. For example, input X is, for example, 1. Then you go line by line and execute your program. For example, if X is 1, then greater less than 0 does not hold. You go immediately to else condition. Then inside else it's greater than 5. Okay, so you just check step by step, and then you go line by line with your particular value. In symbolic execution, it's very similar to algebra example I showed you during the first lecture. The idea that you keep track of all possible conditions, like you see here. So initially, we check if X is less than 0 or not. If it is, then we have one sub-branch. If not, then we have different. So once we checked for this condition, then we have a different check like here or there. It depends whether this is true or false. And so the most interesting and technically difficult case, if we have here not branching condition, but a loop, like while loop. And while loop means that we check this condition each time the loop is executed. So one loop here can transform into a huge subtree on the right. And if loop is infinite, then the tree here will be infinite too. But again, this tree is constructed automatically by a tool. And what we have on every branch, just combination of different conditions which we check during the if, else, or while statement. So every branch corresponds not to single numerical execution, but to the whole class of different numerical executions which correspond to this combination of properties. So, for example, like here, if X is less than -3, for example, it's -4, -5, -6, -7, then for all these inputs, you will go through these two nodes and then go down. So this is basically the idea. And so the tree terminates when the program on the left reaches its terminal point. So finally, here in the leaf, you have just sometimes small, sometimes big combination of different conditions, and then some result, some assignment, what will happen to the state. And that's exactly why we need Z3, because Z3 or similar tool like this are very good for working in this huge combination of simple properties, and that's exactly what's written here. So we simulate behavior of these instructions. I mean, simulate symbolically, and then we use the tree to check what happens on the leaf, and then we switch to the next step to check if the 4 types of bugs I just mentioned are really possible during this particular combination of conditions or not. And then validator is just additional step just to, because sometimes you might get a lot of false positives, which is really annoying and not good. So, okay, questions, comments are welcome. And let's go ahead. So okay, this is a very important part. So let me just maybe repeat again. So once you need to understand what is bytecode, so how, and you see there is another command here on the bottom, which is really important. So in theory, we would prefer to verify source code because we have access to the source code. We can compile it and verify the bytecode. But as you see from this command, in real life, the situation is not that easy. typically people do not provide source code. You just have access to the Solidity, the result of the Solidity compiler. So surely you can kind of apply this technique to kind of reverse engineer and to get this graph. But again, this graph is not really human readable. And if smart contract is not really small, then this graph could be big and very difficult for human analysis. So that's another thing which is important. So first, to understand what's bytecode. Second, to understand what's control flow graph, and that we can build it from the bytecode. The third important notion here is symbolic execution. Again, not sure if my comment was enough for you to understand. Just find a lot of literature and video lectures on this topic, because this is very, very important and very widely used in formula verification. Okay, this is exactly what we have in Agent. And then there is another tool, which is kind of build of this, the first one. So a series, again, you have access to the source code on GitHub because it's open source. So, and as you see, this tool is focused on different bugs, which are arithmetic bugs, like underflow or overflow, truncation, and bugs related to signed, unsigned types of integer. So again, these types of bugs are very standard for all smart contracts. So the authors of the tools did already job for you to specify all the formal requirements to your code to avoid this bug. And then you just feed your code into this tool. It checks whether these conditions are okay or not. So, okay, that's basically all for today. So let me finish with some links to papers. There are a lot of interesting and nice research in this area. Here are just a few links which I used for my lecture. And okay, just feel free to contact me to maybe ask some questions, comments, etc. And here is a link to our final test, which is prepared for you just maybe for self-assessment and to check how you understand the logic here. And again, if you complete it by Wednesday, and then I will be happy to give you certificate from Exactpro for completing this course. Okay, so see you the day after tomorrow for questions and answer session related to this lecture. And okay, thank you. Goodbye.